we're going to talk about module 5 and 6 for today. So as you guys can see, this one is only 14 slides, and then the other one is, if you guys have checked that one already, that one is only 10 slides. So this will only take maybe 2 meetings. So part 1 and part 2. Okay, so let's start now without a further delay. So module 5 will be about superposition theorem, okay, dizzy network analysis. All right, so here's the definition of a superposition theorem. So superposition theorem is one of the genius way, to simplify or solve a complex subject and simplifies it in a way that makes perfect sense. Okay, so like the case, I mean the Kirchhoff's law, the Maxwell or the mesh current method, and this one superposition theorem is one of the best way to eliminate or to simplify complex circuit into in a very simple manner, or a very simple circuit. So the strategy used in superposition theorem is to eliminate all but one source of power within a network at a time. So using series or parallel analysis to determine voltage drops and or currents within the modified network for each power source separately. So when we say superposition theorem, this one is perfect if we have a lot of sources. So if we have, let's say, more than two sources, one voltage source and then one current source, or it could even be, two voltage source or two current source, so any of those two. Okay, so as long as it's more than one source, then superposition theorem is one of the perfect theorem that you can use to, simplify it in a, simple circuit. Okay, so then once voltage drops and or currents have been determined for each power source working separately, the values are all superimposed on top of each other. So added algebraically to find actual voltage drops or currents with all sources active. So meaning, as you guys can see right here, we will eliminate everything and then we will retain one voltage source. So let's say if we have two voltage source, so we're going to have two computation for that. So we're going to eliminate the other voltage source for now, and then we're going to solve the other voltage source. So that's your first computation, and then vice versa. So for the second computation, you're going to eliminate the first voltage source, and then you're going to retain the second voltage source, and then compute that, get the voltage drop, get the current, and then once you've got the results of those two computations, you can now combine them, okay, as one. So once you have combined them, we call that one superimpose. Okay. So for you to have an idea, let's proceed to this example. So one thing that I would like you guys to notice is this example was actually used in our mesh current method, or the Maxwell loop method. So let me just show that one to you. Maxwell. Oops, not this one. This is your lab. All right, so we have used this one before already in Maxwell. So as I guys can see, you have 28, 4, 2, 1, and then 7 volts, which is the same with this example, 28, 4, 2, 1, and then 7 volts. So we are going to prove that, just by using superposition theorem, okay, we can also have the same result, okay? So let me just show to you guys the result here. So we have here 5 amps, okay, on this side, and then we have here negative 1 amp, okay, and then if you're going to combine them, we have, where is the final? Right here. So 5 amps here, 1 amp here, and then 4 amps here, okay, and then of course their individual voltage drops, okay. So we're going to prove that one using a superposition theorem. All right, so let me just minimize that one for now, and then let's take a look on this example. So again, we have two sources, so superposition theorem is perfect for this example. So we have 28 volts and then 7 volts, and then we have three resistors. So since we have two sources of power in the circuit, we will have to calculate two sets of values for voltage drops and or currents So one for the circuit with only 28-volt battery in effect. So as you guys can see, we have only considered the left side part for now, or the left side voltage source, and then we have eliminated the other voltage source. Okay, so here's what you can do. If it's a voltage source, okay, where is that one? Okay, here. So if it's a voltage source, all you need to do is short that one. Okay, so in other words, we call that one make, wherein if you're going to make it, of course, it's now short. Okay, but if it's a current source, okay, all you need to do is the opposite. Okay, so if it's short in a voltage source, then in current, you need to break it. Okay, so you just leave it open. But since this one is voltage source, so yeah, 7 volts is voltage source, so just short that one. Okay, as simple as that. That's the only thing that you need to do to the other sources. All right. So yeah, that's your first step, and then having now this circuit. And here's now the result. So let's have our own solution regarding with this one. So let me just get this one. Okay, so in here, the one that we are looking for, so find I1, I2, I3. So those are the individual currents, and then we also need the voltage drops of those resistors. So VR1, VR2, and VR3. Okay, so we need to solve those six. So let's start. So the first thing that we can do is actually find the total current. Okay, so finding the IT. So in finding the IT, as you guys can see, it's super simple. Just get the parallel of this one R2 and R3, and then you can now combine that one or add that one to this R1 since they are now in series. And then you now have the total resistance. So from there, we already have the total voltage and then the total resistance. Then we can now solve for the total current. So the formula for the total current is IT is equal to VT divided by RT. All right. So in here, if I will simplify this one, let me get another copy. Okay, but let me make this one smaller. So what I will do is I will now, add the R2 and R3 with each other, with the computation of parallel. So I will delete this one, okay, and then this one now will become R2 parallel to R3, okay. So this one now is not 1 ohm anymore. But for us to be able to get the value of this R2 and R3, so we need to solve for that. So R2 parallel to R3, okay, wherein we only have two resistors, so we can use this formula wherein we have 2 times 1 divided by 2 plus 1. Okay, am I correct? So were you guys able to follow on how did we get this expression right here for the parallel of the R2 and R3? Okay. How about the others? Just give me a thumbs up if you guys were able to follow up to this point. And if you have a question, so feel free to ask feel free to raise your hand anytime. Okay. So in here, just use your calculator and you will get 2 times 1 divided by 2 plus 1. So we will get 0.66667, or you just simply say it's 67, 0.67. Okay. So this one is ohms. Okay, I hope you guys can see this one. All right. So right here, we already have the value of R2 and R3, okay, which is 0.67. And as you guys can see, they are now in series. So R1 plus R2 parallel to R3. So that is the uh, result for our total resistance. Okay, RT is equal to R1 plus the value of the R2 and R3. So in here, R1 is 4 ohms, and then the value of R2 and R3 is 0.67. Okay, so for our RT, we have here 4.67 ohms. Okay, so were you guys able to follow up to this point? And how did we get 4.67? Okay, it's good. And then since we now have the total resistance, then we can now solve for the total current. So VT is 28 volts, and then RT is 4.67. So 28 divided by 4.67 is 5.995 or 5.99. Or we could just simply say it's 6 ohms, okay, to be exact. Okay. So you will know later on why did I put here 6. So you could put here 5.99, so they are just the same. But I'll just choose 6 because that is the one that we have, okay, in this table. Okay. So we have 6 ohms, 6 total current, okay, which is this one. All right. Why ohms? That is the reason why I'm doing this. This one is 6 ohms, okay, not ohms. All right. So from here, we could already see that, we have here 6 ohms, and then right here for the I1, okay, this one is now having a current of 6 ohms. So I1 is already answered, okay. But at this point, okay, so we don't know since they will split, okay. Some of the current will go to R3 and then some of the current will go to R2, okay. So what we need to do for us to be able to solve the VR1, VR2, and VR3, okay, so we need this formula first. So VR1 is equal to, so since we are looking for the voltage drop on R1, so we need the I1 times the R1, okay, wherein I1 is already 6 amps, and then R1 is 4 ohms. So the voltage drop across R1 is 24 volts. Okay, so VR1 is now already answered, 24 volts. There you go. Now, so as you guys can see right here, at this point, we have a voltage drop of 24 volts. So 28 minus 24, so you'll get a potential voltage, okay, of 4 volts. So we could say that this is our node A. So in order for us to get the voltage that is remaining after passing through this R1 right here, so we could say that VA or voltage at node A is equal to total voltage minus VR1. Okay, wherein VT is 28 and then VR1 is 24. Wherein we will get 4 volts as our potential voltage after passing through this voltage drop. So that is why this node A right here is equal to 4 volts. So we already know that, some voltage will go here, some voltage will go here. But if you guys are going to take a look on this one, they are actually in parallel. Okay. So again, in parallel, whatever is the voltage that is passing through here is the same or equal with the voltage that is passing through here, as long as they are in parallel with each other. Okay. So that is why we could already assume that VR2, okay, is equal to 4 volts, and at the same time, VR3 is equal to 4 volts. Because we already know that, we have 4 volts that will pass through here, and then 4 volts another that will pass through here, and then going back here will be 0. Okay. So we could also apply the concept of KVL. Okay, after passing through all of those loads or resistors, as soon as it goes back to this original source, it is now equal to 0. Okay. So were you guys able to follow on how did we get this VR2 and VR3? What about the others? Again, it is a concept of parallel. Okay. So if we don't have this R1 right here, then we are sure that, we have 28 volts passing through here and then 28 volts passing through here. But since we have series connection right here, then of course we have to deduct that voltage drop in here. Okay, so we already have answered the VR1, VR2, and VR3, okay, which is 4 volts and then another 4 volts. Then the one that we are now looking for is the I2 and I3. Okay, so for the I2, so it's now very simple. Okay, so we need the voltage, uh, say VR2 to make it consistent. Voltage across R2, and then of course, uh, I2 R2, yeah, the resistance. So VR2 is 4 volts, and then for the R2 we have 2 ohms. So 4 divided by 2 is 2 amps. So that is now the current that is flowing right here. Okay, so 6 amps and then 2 amps. And then from here, just by using KCL, we could already see that, so we have 6 amps here and then 2 amps here. So the remaining 4 amps will go to R3. Okay, but just to show it using a Ohm's law formula. So let's do that one. So I3 is equal to VR3 divided by R3. So VR3 is 4 volts and then R3 is 1 ohms. So there you go. So 4 divided by 1 is 4 amps. Okay. So if you're going to check this one using KCL at node A. Okay. So we have here the I1 that is entering this node, and then I2 leaving, and then I3 leaving. So I1 minus I2 minus I2 is equal to 0. So if you're going to, transpose this I2 and I3 on the other side, you will have this kind of expression plus I3, okay, which is actually correct. Okay. So I2 is 2 ohms and then I3 is 4 amps. So 2 plus 4 is 6, which is equal to our I1 or I total. So there you go. So were you guys able to follow on how did we get those individual currents and individual voltage drop? Okay. Very good, Mr. Labson. How about the others? Anyone who has a question? Okay, very good, Mr. Awas. So very good, Mr. Ramos. Very good, Mr. Mendoza. Okay, very good, Mr. Panicala. Agustin. How about Mr. Mina? Mr. Aral? Okay, very good. Mr. Francisco. Miss Chelsea. Miss Ventura.
Yes, sir.
Okay. So I'm clearing the things that you might have a question right now because I am now going to erase this one. Okay. So I won't be able to explain this one anymore since we don't have enough space, and then we will proceed now on the second set, which is solving for the 7 volts. Okay, so I hope everything is clear because I will not explain this one anymore. Okay, so if you're confused, so you can always uh, watch this recorded video and yeah, just watch it again and try to analyze it again. Anyway, so let's try to compare now our answer to this table right here. Okay, so maybe I'll just put it right here. All right, so we have here the voltage, the current, the resistors, and then we have here the R1, R2, R3, so individual currents, individual voltage drop, and then we have here the parallel uh, result of the R2 and R3, and then the total results of those. So let's start right here on the total. So we already have the 28 volts as our total voltage. And then we have here the 6 amps as our total current. And then we have here the 4.667 as our total resistance, which is this one. Okay, so only here yet get the 3 decimals, but in our case, we only get the 2 decimals. Okay, and then for the parallel value of R2 and R3, which is 0.67, okay, which is just the same with this one. And then we have here the uh, what do you call this one, voltage, okay, that is passing through this R2 and R3, which is 4 volts. So it's the same. And then, of course, once we have combined them, so we are now in series connection. So as you guys can see, we now also have here 6 amps in total. Okay, so 6 amps for the R1, and then 6 amps for the R2 and R3. Okay, so 6 amps for the R1. And then if you're going to separate those, so we have here the 2 amps for the uh, 2 ohms, and then 4 amps for the 1 ohm. Okay, so yeah, that's it for the current. And then for the total voltage, I mean the voltage drop rather. So we have here 24 volts across R1, so that's the voltage drop. And then up to, reaching the R2 and R3 since they are in parallel, so it's 4 volts per volts. And then we have here the value of resistance. So R1 is 4 ohms and R2 is 2 ohms, and then R3 is 1 ohm. So yeah, there you go. This is just the summary of our answers, okay, in which they are the same. Okay, so before I will delete everything in here, so do you guys have a question so far? Anyone who has a clarification? All right, so I guess none. So let me now erase this one, and then let's now proceed to the second one. Okay, so in here we are now going to deal with the 7 volts. Okay, so here's the result for this one. So the same, you're going to find the individual currents and then the individual voltage drops. VR1, VR2, and VR2. Okay. So the same process. So the first thing that we need to look for is the total current. Okay. So IT is equal to VT divided by RT, wherein in here, RT is equal to the R1 parallel to R2 plus RT. Okay. So let me just again create another simplified version of this one. Oops. Okay. So I will delete this one to make everything in series connection. Okay. And in here, this is not R1 anymore, but this one now is R1 parallel to R2. R1 parallel to R2. Okay. Okay, let me try to use this extractor instead of using, paint. All right. So in order for us to get the value of R1 and R2, so again, we need the formula. No, it's difficult to have a numerator and denominator regarding this one. Anyway, let's try. So 4 times 1 divided by 4 plus 1. Okay. So in here, if we are going to simplify that one, I think it's much more difficult to use this one. Anyway, okay, so 4 times 1 is 4, and then divided by 5, 4 divided by 5 is equal to 0.8. So this one is equal to 0.8, okay, ohms. Okay, so that is now the value of your R1 and R2, 0.8. So from here, you can now combine the R1, R2, and R3. for you to be able to get the R total. So R total is equal to R2 parallel to R1 parallel to R2 plus R3, wherein R1 parallel to R2 is equal to 0.8 and the R3 is 1 ohm. So for the R total, we have here 1.8 ohms. Okay. So in here, we already have the value of R total, so we can now solve for the value of total current. So V total is 7 volts. So 7 divided by 0.8 is equal to, so we have here 8.75 amps. So I hope you guys are also checking my answers using your own calculator. Okay. So were you guys able to follow up to this point? 8.75 for the total current. Okay, very good. So as you guys can see, so we have here the I total, which is now equal with our I3. Okay. I3 is equal to 8.75 amps. Okay. So now we can now actually solve for the value of BR3 since we now have the value of I3. Okay. Ah, all right. So very good, Mr. Agustin. So why did I only write here 0.8? Because, what we write here is 1.8, not 0.8. So thank you for that one. So this one is not 8.75. Okay. Very good, very good. And this one is not 0.8, but this one is 1.8. And of course, this one now is not 8.75. So 7 divided by 1.8 is equal to 3.88889. Or we just simply say that this one is 3.89. Okay, so we still have 2 minutes left. Okay, which is now the same with our I3. Okay, I3 is 3.89 amps. Okay, are there more questions? Okay na, teka lang. 4 times 2. Oh, I see. See, I have a lot of mistakes. So thank you, Mr. Agustin and then Mr. Mina for, where is my cursor? Right here. So this one should not be 4 times 1, but this one should be 4 times 2 and then 4 divided, divided by 4 plus 2. We have a lot of mistakes. Okay, let me erase this one, and also this one, and also that one. Okay, so in here, and of course this one also. So here we have R1 parallel to R2, wherein we have 4 times 2 divided by 4 plus 2. So 8 divided by 6 is equal to 1.33. So this one is 1.33 ohms. 1.33 ohms. And then for the R total, we have here the R1 parallel to R2 plus R3. So R1 parallel to R2 is 1.33 plus R3 is 1 ohm. So this one is 2.33. And then for the B total, it's still 7. And then RT is 2.33 ohms. Okay. So 7 divided by 2.233 is 3 amps. All right. So we will stop here for now since we don't have enough time anymore. So we will just continue the rest on the part 2. Okay, so goodbye for now and see you guys later. Alright, so can you guys see my screen now?
Yes, sir.
Okay, and also just give me a thumbs up, so just to let me know that you guys are already in front of your computer. Okay, so 1, 2, 3, 4, 5, 6, 7. Okay, so maybe at least half of you are already here. Anyway, so the others will just catch up to us. So in here we can now see that I3 is also equal with I total, which is 3 amps. Okay, and then since we already have the value of I3, so we can now solve for the value of VR3, or the voltage drop across R3. So VR3 is equal to I3 times R3, wherein I3 is 3 amps and then R3 is 1 amp. I mean 1 amps. Okay, so in here 3 times 1 is 3 volts, right? So there you go. So at this point, okay, so if you are going to, get the potential voltage, so it's the same process just like what we did a while ago. So in order for us to get the voltage at point A, so we need to get the V total minus the VR3, okay? Wherein V total is 7 volts, and then VR3 across here is 3 volts. Okay, so this will give us a result of 4 volts. So at this point, we have a value of 4 volts. And the same analysis, just like what we did a while ago, since they are in parallel. So R1 has a voltage drop, or a voltage that is flowing in here, which is 4 volts. And the same with R2, which has also a voltage drop, or a voltage that is flowing here, which is also 4 volts. So we could say that VR1 is equal to VR2, which is equal to 4 volts. Okay, so from here we already have the VR1, I mean VR3. Okay, let's write the VR3, which is 3 volts. And we also now have here the VR1 and VR2, which is equal to 4 volts. And then since we already have the value of VR1 and VR2, so we can now solve for the value of IR1. I3 is already here, I1. Okay, so the formula for I1 is VR1 divided by R1. So for the VR1, we have here 4 volts divided by R1, which is 4 ohms. So 4 divided by 4 is 1. So for the I1, we have 1 amp. And then for the I2, okay, so again, since we already have the value of I3 and I1, we can now solve for the value of I2 using KCL. But just to be consistent, we're going to apply the formula of Ohm's law. So I2 is equal to VR2 divided by R2. So VR2 is still 4 volts divided by R2, which is 2 ohms. So 4 divided by 2 is equal to 2 amps. Okay. Let me just remove this one for consistencies, since I didn't put here the units. So we have here 2 amps for the I2. Okay, so let's verify this one using KCL. KCL at node A. So as you guys can see, we have here I3, which is entering this node A, and then I2 and I1, which is leaving, okay, the node A. So I3 minus I1 minus I2 is equal to 0. Or I3 is equal to I1 plus I2. So what is our I3? So I3 is 3 amps. And for the I1 and I2, which they have a value of 1 amp and 2 amps. So 1 plus 2 is 3 amps. So uh, our values of our currents is correct. Okay, so there you go. We now have the value of I1, which is 1 amp, and then I2 is equal to 2 amps. All right, so there you go. So we now have answered all of the individual currents and then the individual voltage drops. And then let's see if we have the same results by comparing that one to this table. Okay, so let me place it right here. So let's just base it right here. So for the total uh, current, so we have 3 amps. Total voltage is 7. And then for the total resistance is 2.33, which is 1. And let's proceed to right here. R1 parallel to R2 is 1.33. And then the voltage drop across R1 is 4 volts. Okay, which is this one. And for the current that is flowing on I1, uh, R1 and R2, okay, that's the combined value of R1 and R2. So 1 amp plus 2 amp is 3 amps. And we have here the voltage drop across R3, which is 3 volts. VR3. There you go. So we have here 3 volts, or you see me, this 1, 3 volts. And what else? So we have here the current, okay, on the R3, which is 3 amps, and the voltage drop, and then the resistance, okay, which is 1 ohm. And then moving on to the R2, so we have here a voltage drop, which is 4 volts. There you go. And then 2 amps for the R2 or I2 right here. And then 2 ohms for its own value of resistor. And then for the R1, so we have here 4 volts, okay, across R1. And then 1 amp across I1. And then 4 ohms on that resistor. So yeah, we have the same results, which is only saying that we've got the same, I mean, we've got the correct answer. So were you guys able to follow on how did we get those values? Okay, very good. What about the others? Okay, so maybe at least half of you are able to get it. So again, if you have a question, so feel free to ask me anytime. All right. So once you already have the results in the first set and then the second set, then you can now combine them. Okay. Again, once you combine them, we call that one superimpose. Okay. So by superimposing, so when superimposing these values of voltage and current, we have to be very careful to consider polarity of the voltage drop, okay, and direction of the current flow as the values to have to be added algebraically. Okay, so in here, in order for us to compare it as clear as possible, so let me just get this table right here. So that is the reason why they are in table, to easily compare and add them together. Put it right here. And then here's the second table. And for the superimposed values, oops, not this one. We have this one. So this one is only for the voltage. So we have another table for the current. But let's have the voltage uh, values for now. Okay, so as you guys can see right here, we're going to deal with the final, oops, not this one. Okay, so maybe it's better if we are going to get both of the tables. So we have here for the first table, okay, let me shrink this one. And we have here the second table. Anyway, so I hope you guys can still see this one. So one thing that you guys need to check is the polarity. So notice that we have here positive, negative, and then we have here negative, positive. So if you guys are going to take a look on this one, we have a current that is, flowing in the side, and then we have a current that is flowing on the side. So upon, meeting on the middle, okay, so you guys already know that they will not be added to each other, okay? So there will be a collision wherein, of course, whoever, the larger values will dominate that path or that node. So it's quite obvious already. So it is the B1, or the left side voltage, that is the one that is going to dominate the entire flow of current. Okay, so that is why I've got, if you're going to compare it right here, we have here positive 24 volts, and then we have here minus 4 volts. So how did we know that, it's 24 minus 4, or not 4 minus 24? So one rule of thumb, when it comes to voltages, so it's always the higher voltage minus the lower voltage. So assuming that, both of them have a positive polarity, or positive signage. Okay, so it's always like that. Higher voltage minus lower voltage. So in here we have 24 volts. I mean, not 24. Is it right? Yeah, 24. So we have here 24 minus 4 volts. Okay. So there you go. Having this 124 minus 4 is equal to 20 volts. So, the one that, dominates this uh, node A right here is the left side, wherein the final circuit, I mean, the final value of this one is 20 volts. Okay. So the same with the ER2 and ER3. Okay. So for the ER2, we have here 4 volts, and then for the R2, we still have 4 volts. But if you guys are going to take a look on this one, so our current on, where is this one? Okay, for the R2, okay, so on the left side, we have this current flowing right here, and then on the right side, we have this current flowing right here. So they have the same polarity. So positive, negative, positive, negative. So from here, you could already see that they will be added with each other. Okay. So from here, so R2 plus R2. So you don't need to, see the outer sign, or the entering sign of that one. So it's always positive. We don't have a negative voltage. Okay. So it's always positive. So in here we have 4 volts plus 4 volts is equal to 8 volts. Okay. And then for the ER3 right here, so we have here 3 volts, and then we have here 4 volts. So again, the same concept. The higher the voltage, it is the one who's going to dominate the path or the branch. So we have here 4 volts minus 3 volts is equal to 1 volt for our RT. Okay, so these are now the final values for our R1, R2, and then R3. Okay, so if you guys are going to get the final circuit for the voltages, we have this one. Let me just shrink this one and fill it right here. Okay, so we still have the 28 volts and then 7 volts, but once you're going to combine their voltage drops, we have here 20 volts. Where is that? 20 volts for the R1, and then 8 volts for the R2, and then 1 volt for the R3. Okay, so this is now their final voltage drops, okay, or the voltage across this entire circuit. So were you guys able to follow so far? Okay, Okay, so let you guys, take a look on your screen and then analyze everything. Again, to avoid confusion, all of their values are positive. Okay, so the one that we are considering here is the flow of current. So if they have, different flow, so of course, whichever, uh, whichever is higher, that is the one who's going to dominate the entire flow of current. Well, that only happens on our R1 and R3. Okay, so any questions so far? Anyone? So feel free to raise your hand. Okay, so one more time. So just give me a thumbs up if you guys were able to get it. Just to let me know how many of you were able to follow up to this point. So 1, 2, 3, 4, 4 only. 5, 6, 7, 8, 9. Okay, so 9 out of how many? 9 out of 15 or 9 out of 14. Anyway, so again, I hope to the others who still wasn't able to follow, I hope you at least get the idea and then just review this one, once our discussion is over. So that's it for the voltages. So let's now proceed to the current. Okay. So let me just erase this one. Coding this one. Okay, and let me get this one. All right. So the same method. So we have the IR1 right here, the final current on R1, the final current on R2, the final current on R3. So if you're going to start with R1, so it's very obvious that we have, different polarity. So we have 6 amps going here and then 1 amp going here. So it is now obvious that, whichever the one is highest, okay, is a one, higher rather, not highest, higher is the one who's going to dominate the flow of current. So IH minus IL. So in here we have 6 amps minus 1 amp, which is equal to 5 amps. Okay, so this is the answer for the I1. Okay, so as you guys can see right here. And then for the R2, so it's noticeable that we have the same flow of current, so they will be added with each other. So we have here, so R2 is 2 amps, and then I2 on the other side is still 2 amps. So 2 plus 2 is equal to 4 amps. Okay, so I hope there's no problem when it comes to R2. But for R3, so again, they have different flow of current. So one is going on this side, and then another one is going in from here to there. So in here we have, where is our R3 and current? So we have 4 amps for this left side, and then 3 amps for the right side. So 4 minus 3 is equal to 1 amp. Okay, so that's how we've got those results. All right. So I hope you guys were able to get the idea. Okay, and then also the final currents. So are we clear so far? So just give me a thumbs up if it's okay, or if it's no, just raise your hand. Yes, Mr. Awas, if it's the same direction, add. If they have different direction, of course, this will be applied. IH minus IL. Okay, so of course the value of this IH is positive, and then the value of this IL is also positive. So you don't need to worry about the the signages of these values. Everything is positive. Okay, so that is why it is highlighted in here that we are only talking about DC network analysis. So in DC we don't have negative currents. Okay, so that will only happen in Kirchhoff's law, since we have a different assumption when it comes to polarity. But in reality, that is positive current and then positive voltage. Okay. Well, we're only going to have a negative value of current and voltage if we are dealing with AC analysis. Okay, but since we are only dealing with DC, so it's always a zero or above, zero or positive only. Okay, so negative, no negative uh, values of currents and voltages. Okay, so here is also the final circuit flow of current. Okay, so we have 5 amps right here, 1 amp right here, and then 4 amp right here. So it is now obvious that this 28 volt will dominate this 7 volt right here, wherein is now like this 7 volt is being charged by this 28 volt right here. Okay, so there you go. This is now the final superimposed values for current and then for the voltage. Okay, and yeah, that is actually the simplest example, okay, that I can give to you when it comes to superimpose. So if you want to learn more about position theorem, so feel free to visit these two YouTube link. Okay, so this will give you more explanations, more examples, okay, to learn more about superposition theorem. Okay, and then here's just the summary and the review. So superposition theorem works only, okay, for circuits that are reducible to series parallel combinations. For each of the power sources of a time, thus this theorem is useless for analyzing an unbalanced bridge circuit. So if you want to solve unbalanced bridge circuit, so you can use mesh current method or the Maxwell loop method. Okay, and it only works where the underlying equations are linear. Okay, so that is their main differences. So if a circuit cannot be simplified using Ohm's law, okay, series parallel connection, then you have to use a mesh current method or the Kirchhoff's law, either of those two. But if it's if it can be simplified uh, they using a series parallel connection, and then it has a lot of voltage source or current source, then you can use superposition theorem. Okay, so that is the limitation when it comes to superposition theorem. Unlike in mesh current method, you can solve anything. Okay, so the requisite of linearity means that the superposition theorem is only applicable for determining voltage and current, so not power. Okay, so we can only solve the voltage, or the individual voltage and then individual current, okay, using the superposition theorem, but not the power. Okay, that is why we don't have an example when it comes to solving a power in superposition theorem. Okay, so being nonlinear, functions do not algebraically add to an accurate total when only one source is considered at a time. Okay, so the need for linearity also means this theorem cannot be applied in circuits where the resistance of a component changes with voltage or current. Hence, networks containing components like lamps, incandescent or gas discharge, or various varistors could not be analyzed. So the same with capacitors and inductors. So superposition theorem can only be applied if we have linearity. So when say linear, so it's 1:1. So if we have a raise in current, the voltage will also go up. But if we have capacitor, so even though you're already raising your voltage, but the current is still the same. So that is not linear anymore. Okay, we call that one non-linear. So if you want to learn more about linearity, okay, so feel free to search on YouTube. So it might explain it to you in 1 to 2 to 3 minutes. Okay, or to make it simple, when we say linearity, so we only have these three components, okay, that we could consider: the voltage source, okay, the current source, and then the resistor. Okay, so if we have capacitor, inductor, and any other component which is not linear, okay, then that one is not linearity anymore. Okay, so take note, we only have three components when it comes to linearity. Okay, resistor, voltage source, and then the current source. Okay, so I hope we're clear with that one. So any questions so far? Okay, so yes, no question. So another prerequisite for superposition theorem is that all components must be bilateral, okay, meaning that they behave the same with electrons flowing in either direction through them. So I'm say bilateral. Okay, so if you guys are going to take a look on this one, what we did in here is conventional method. Okay, the same with this one, conventional method. So if you're going to solve this one using electron method, okay, so it's the other method, so it's counterclockwise. Okay, the same with this one, it's now in clockwise. So it should give you the same result. Okay, because if not, then there must be something wrong with your solution or your answers. Okay. And the superposition theorem finds use in the study of alternating current (AC) circuits and semiconductor amplifier circuits, where sometimes AC is often mixed, superimposed with DC. Okay, so yeah, you can also use superposition theorem as long as it's only pure AC with no capacitor and inductor. Okay, it's just that we have a sine wave instead of a direct current. So you can also apply superposition theorem. Okay, so just a review again, the superposition theorem states that a circuit can be analyzed with only one source of a power at a time. So the corresponding component, voltages and currents algebraically added to find out what they'll do with all power sources in effect. So to negate all but one power source for analysis, again for the voltages, replace any sources of voltages or batteries with a wire or just short it. Okay, and then for the current source, replace any current source with an open break, okay, or just break it. And then here are the references for this presentation. So we have three. One is for the all about circuits, which all of the information right here came from this website. And then we have another two related references. So just in case this explanation that came from all about circuits is not enough, feel free to visit the tutorials point and then the circuit globe. Okay, so they have another approach, another way of explanation, okay, in which it might enlighten you to understand more about superposition theorem. Okay, so yeah, that's it for the superposition theorem. So are we clear so far? So just give me a thumbs up if everything is okay. Okay, okay, okay. All right, so very good. So please half of you. How about the others? Okay, so I have mentioned that it might only took us 2 meetings, but it seems that we might uh, not be able to finish the module 5 and 6 with 2 meetings only. So we have to extend up to part 3. Okay. So anyway, without a further delay, let's now start with the revised module with the module 6, which is a nodal voltage analysis. So don't you guys worry. If superposition theorem is already easy and simple, though it's only uh, time uh, allotment, so you need to allot of time because you have to solve if you have three sources, then you have to solve three set. If you have four sources, then you have to solve four set also. Okay, but in here in nodal voltage analysis, so it's only one time. Okay, one time big time. So in nodal voltage analysis, so we are dealing with nodes. So we have VA, VB, VC, and then VD. Okay, so the same things that we can find on the superposition theorem. We can also find the individual currents. We can also find the voltage drop for the R1, R2, and R3. Okay, it's just that it has its own analysis and ways of solving things. So nodal voltage analysis finds the unknown voltage drops around the circuit between different nodes that provide a common connection for two or more circuit components. Okay, so let's have this example as as our basis in solving nodal voltage analysis. Okay, but before that, let me just clarify things. So if in a superposition theorem, we are applying KCL, we're applying series parallel law, the Ohm's law. In here, we are only applying KCL and then Ohm's law. Okay, well, to be exact, as long as you know the KCL, that's already enough for you to be able to solve the voltage or nodal voltage analysis. Well, of course, with a little bit help of Ohm's law. Okay, so nodal voltage analysis uses the nodal equations of Kirchhoff's first law or the KCL to find the voltage potentials around the circuit. So by adding together all these nodal voltages, the net result will be equal to zero. Okay, so from the first node to second node to third node and so on and so forth. So at each node point, write down Kirchhoff's first law equation. That is, again, in first law, the current that is entering a node are exactly equal in value to the currents leaving the node. Okay, positive for the entering and then negative for the leaving. Okay, then express each current in terms of the voltage across the branch. For n nodes, one node will be used as a reference node, and all the other voltages will be a reference or measured with respect to this common node. Okay, all right, so let's now start with this example. So what I will do is I will get this one now and then have our own solution. So uh, in this presentation, it has its own solution. Okay, but in my case, I will just explain from the very start so that we can understand everything step by step. Okay, so in nodal voltage analysis, so this one is super simple actually. All you need to do is apply KCL at node VB. Okay, so in here we have I1 going in. So I1 positive and then I2 going in or entering. So it's plus I2. But in here we have leaving. So minus I3 is equal to 0. Okay. So this is very, very important. This is now your basis or reference when it comes to solving for the unknown variables. Okay, in this current. I mean in this circuit. Okay, so let me just recall or write here the Ohm's law. So I is equal to V divided by R. Okay, so the same concept with this one, wherein I1 is equal to the voltage drop across this one, VA and VB, okay, divided by R. Okay, so let me just write down again the rule, okay, when it comes to getting the potential voltage. So we have here the VH or the higher voltage minus the VL, okay, for us to get the VR1 or the voltage drop across that R1, okay. So in here, the same method just like what we did a while ago, we could have here VA minus VB, okay, is equal to VR1. Okay, so again, how did we know that VA is the higher voltage than our VB? Because we have this flow of current right here. Okay, assuming that we have 10 volts right here. So of course, after passing through this voltage drop, then we now have a lesser voltage at this point at node VB. Okay, so that is why we have here a expression VA minus VB. Okay, so in here we're just simply going to put it right here as our for the voltage. Okay, the final voltage across VB. So we have here VA minus VB, okay, divided by R. So what is this R? Let's just name this one as our R1, R2, and then R3, okay, divided by R1. So there you go. That is now our first expression for the I1. Okay, so since we don't have enough time again, we will just continue the rest on part 3. So again, goodbye for now and see you guys later on part 3. Waiting time. Okay, so can you guys see my screen now?
Yes, sir.
Okay, so great. Okay, so just give me a thumbs up just to let me know that you guys are already in front of your computers. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 11. All right, so 11 out of 14. Okay, so yeah. So we now have here VA minus VB. So VA minus VB is our voltage drop or the voltage across this R1. So are we clear so far on how did we get this VA minus VB divided by R1 right here? Anyone? So just give me a thumbs up just to let me know that you were able to get this one. All right, so how about raise your hand if you didn't get it? None. So there were only two who gave me thumbs up. So I'm pretty sure that most of you are confused or you know maybe still didn't know how did we get this expression right here. So again, this one came from the Ohm's law formula. So I is equal to V divided by R. So if you're going to get the I1, so I1 is equal to V1, of course, divided by R1. Wherein the one that we're talking about, the V1 right here, this one is actually the voltage drop or the voltage across R1. Okay, wherein in order for us to get the value of VR1, okay, so we can use this uh, rule wherein we have the higher voltage lesser the lower voltage. Okay, wherein the higher voltage in here is the VA and then the lower voltage is VB. Now again, how did we know that the higher voltage is VA and not VB? Because if you guys are going to take a look on this one, okay, assuming that we have 10 volts in here, okay, so we already know that VA has a 10 volts, and as soon as it passed through this resistor right here, of course it will give us a voltage drop with a value of we didn't know yet. Okay, so you already know that at this point, VB node VB, this one now has a lower voltage than VA. Okay, so that is why we have here VA minus VB, which is equal to our VR1. And if you guys are going to take along this one came from here. And then if you're going to substitute this VR1 right here, you will get VA minus VB divided by R1, which is now the same with this one. So I hope that one now is clear. So is everything okay now? Okay, how about the others? Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So 8 out of 15 maybe? Or 9 out of 15. So at least half of you were able to get this one. Yeah, anyway, so let's proceed to our I2. Okay, so just get this one since, so again, this is our reference. Okay, so this is already our I1. Okay, next one is the I2 right here. So same concept. So if we have I2 is equal to V2 divided by R2, wherein V2 right here is actually the VR2 or the voltage drop across R2. So we have here VR2. So the same concept in getting the VR2, we have here the VH, higher potential voltage minus the lower potential voltage. So for the R2 right here, so as you guys can see, we have here VC, okay, receiving a 20 volt. And at this point, so of course, it will leave a voltage drop. And then upon reaching VB, so VB now is lesser than VC. So we already know that VC is higher than VB. So in here, we could say that VR2 is equal to VC minus VB, okay? Which is now the same with our VR2 right here, okay? Wherein you can now use this I2 right here to put it as our final expression on this uh, solution or expression. Okay, so we have here VC minus VB divided by R2. Okay, so are we clear? Are you guys able to follow? Okay, only three. What about the others? So 4, 5, 6, 6 out of 15. How many are we? Yeah, 15. 6, 7, 8, 9. So 9 out of 15. Okay, that's good. Okay, so in here, this is one thing that you guys need to know. Okay, so in nodal voltage, okay, the one that is connected to, the negative part, okay, of our batteries or voltage source, that is the one that we call the reference node or the ground node. Okay, so as you guys can see right here, the one that is connected on the negative side is this node B, and then the same with this one on the negative side or the electron side is this D. So we could already say that, as we all know, ground is always a 0 volt, okay, or the reference node is always equal to 0. So in here, we already know that VD is equal to 0. So we can actually use this that one already. Let me just move it right here so we can have more space for our I3. So the last one is minus I3, okay, wherein I3 is equal to VR3 divided by R2, okay, wherein VR3 right here, so the same concept, we have the higher voltage minus the lower voltage. So as you guys can see, we already know that VB is 0, so VB has at least a little bit value of voltage, so VB is our higher potential voltage. So VB minus, okay, VB, okay, which is actually 0, okay, divided by R2. And you can now substitute this one in here. Okay, oops, is this R2? No, R3, sorry. This one is R3 also. So for the I3, we have here VB minus VD, oops, divided by R3 is equal to 0. Okay, And then from here, you can now substitute the given values, okay, of those uh, variables. So we already know that VA is equal to 10 volt, okay, and VB, so we don't know the value of VB since, it will be finalized once we already have the values of everything. Okay, so let's just leave it as VB. And then R1 is 10 ohms plus. So VC is 20 volts because that is the one that is passing through this node. So 20 minus VB, so we don't know the value of VB, so we'll just leave it like that. And divided by R2, which is 20 ohms minus. So VB, so we don't know yet. All right, so let me just make everything capital for consistencies. And okay, let me erase this one and make it capital. This one is VD. Okay, and as you guys may already know, VD is equal to 0, so we could just put here, or we could just leave it as like that, since it will not affect the voltage VB since it's equal to 0. So minus VB divided by R3, so R3 is equal to 40 ohms, is equal to 0. And as you guys can see, we only have one unknown variable. Okay, so if we only have one unknown variable, so we can now solve for the value of that unknown variable. So in my case, what I will do is I will multiply this one by 40 to eliminate the denominators. So 10 or 40 divided by 10 is 4. So that's times 4. 4 times 10 minus VB. Okay, plus. So 40 divided by 20 is 2. So that's multiply to 2. 2 times 20 minus VB. Okay. And then 40 divided by 40 is 1, or this will just simply cancel, minus VB. Okay, is equal to 0. And then from here, you can add similar terms, or you can distribute first rather. Okay. So 4 times 10 is 40 minus 4VB plus 2 times 20 is 40 minus 2VB. And then minus VB is equal to 0. And then from here, you can now add similar terms. So 40 and then 40, so both of them are positive, so it will give us 80. And then minus 4 and then minus 2VB and then minus 1VB, which will give us negative 7VB is equal to 0. And then from here, you can transpose this one on the other side, 7VB, and then you can now solve for the value of VB. VB is equal to 80 divided by 7, which is equal to 11.43, okay, volts. So there you go. You now have the value of VB. And then since we already have the value of VB, we can now solve for the value of I3. Okay. So in here you can actually already solve the value of uh, the I1 and then the I2, since VB is now already given. You can just use this formula. Okay. So let's try to solve the value of I1. So I1 is VA minus VB divided by R1. So let's see what is the result of that one. So VA is 10 volts minus VB is 11.43, okay, divided by R1, which is 10. So whatever is the result of this one, that is our I1. Okay, 10 minus 11.43 divided by 10. So this one will give us negative 0.143 amps. Okay, so this is our I1. And then for the I2, okay, so again, you can get this one, VC minus VB divided by R2 to get the value of I2. So VC is 20 minus VB is 11.43 divided by what is our R2, so it's 20. So this will give us a value of 0.4285 amps, which is now, this is your I2, or equal to I2. And then for the last one, for the I3, so that is VB, okay, divided by 40. So VB is 11.43 divided by 40. 11.43 divided by 40 will give us a result of 0.28575 amps. Okay, this is now our I3. Alright, so there you go. And then from here, you can also solve for the VR1, VR2, and then VR3 since we now have the individual currents. So I will not show those anymore since they are very obvious. So VR1 is equal to I1 times R1. Okay, so VR2 is equal to I2 times R2. And then VR3 is equal to I3 times R3. All right. So yeah, actually our main goal here is just to get the, the voltage across VB and then the current across that VB, which is this one, 0.28575. So were you guys able to follow so far up to this point? Okay, very good. So three only. What about the others? 3 out of 14, 4 out of 14, 5, 6, 7, 8, 9. Okay, very good. At least half of you were able to get the idea. Okay, so if we are going to compare that one, oops, not this one right here. So yeah, the I3 is 0.286 amps. And there you go. So this one is 6, so it only gets the 3 decimals. And yeah, and VB is 80 divided by 7, wherein 80 divided by 7 is equal to 11.43, okay, which is this one. All right. And then the rest are just, bonus, wherein you can solve for the I1, I2, I3, VR1, VR2, and VR3. Okay, so that's it for the first example. So let's have one more example. So in here we have a voltage source and then a current source. So before we are only dealing with two voltage sources, but right now we are now going to deal with a voltage source and then a current source. So in here, same thing. We need to find the I1, I2, I3, VR1, VR2, VR3, and then VA, VB, and then VC. Okay. So notice that VD is, didn't include here because VD is always equal to 0. That is our reference node or our ground node. Okay. So in here, again, just same method as apply KCL first, wherein we have here I1 going into VB, I2 going into VB, and then I3 leaving, okay, which will give you this result right here. And then if you're going to transpose this one on the other side, it will give us I1 plus I2 is equal to I3. Okay, so are we clear so far up to this point? Again, okay. But anyway, so I hope everything is clear on this one since this one is super straightforward. And then again, what we are looking for is the value of VB because once we have solved the value of VB, we can now solve the value of VR1, VR2, VR3, I1, I2, and I3. Okay, so the same method. Okay, so we're going to apply the formula of I is equal to V divided by R, and then in here we're going to look for the I1 first, right here, which is equal to V1 divided by R1, or this V1 right here is actually our VR1 or the voltage drop across R1, okay, wherein I1 is equal to VA minus VB. So again, the same concept. We have here VA minus VB because we know that VA has a higher voltage than VB. Okay, so we can use this one already for our I1. So VA minus VB divided by R1. And then for the I2, so the same concept. So we have here VC minus VB divided by R2. So there you go, VC minus VB divided by R2. And then for the I3, okay, so we have here uh, VB minus VD divided by R3, which is now this one. And then from here, you can now substitute the given values or the given variables. So VA is 30 volts, okay, minus VB. So VB, we don't know that one, so we'll just leave it as it is. And R1 is 5 volts, I mean 5 ohms, which is now this one. And then for the I2, so notice that I2 is already given as a current, so we don't need this one anymore. Okay, we can just simply say that, I2 is 3. So that is why we have plus 3 right here. And then for the VB, so just leave it as it is, so since we don't know the value of that one. And then for the VD, so just minus 0 divided by 3. Okay, so are we clear so far up to this point? Can you guys still follow, or am I too fast?
Yes, sir.
Okay, all right. So if you have a question, so again, feel free to raise your hand, and then let's talk about your concern. All right, so no question. All right, so let's proceed to the next solution. So in here, my goal here, and why did I put here 15, is I wanted to eliminate the denominator. Okay, so just multiply everything by 15, and then you will get this one. So 15 divided by 5 is 3. So 3 times 30 is 90. And then just multiply that 3 to this VB, so it will give you negative 3 VB. Okay. And then for the next one, so 15 times 3 is 45. And then for the last one, so 15 divided by 3 is 5. So it will give us 5 VB. Okay. And then from here, just add similar terms. So 90 plus 45 is 135 minus 3 BB is equal to 5 BB. And then from here, we can transpose this on the other side so that we can add similar terms. So 135 is equal to 5 BB plus 3 BB is equal to 135 is equal to 8 BB. Okay. And then from here, we can now solve the value of BB. So BB is equal to 135 divided by 8, which will give as a result of 16.875 volts. So I hope you guys are using your calculator right now to verify whether this one is correct or no. So please check. Do you guys have the same result, 16.875 volts for our VB?
Same, sir.
Very good. So now, since we already have the value of VB, okay, we can now solve for the value of I1, I2, I3, so any of those that, you can solve first. But in here, we can now solve for the value of I1, okay, which is, using this formula, we have VA minus VB divided by R1. Okay, just substitute everything, and then you will get 2.625 amps. And then for the I3, so the same concept. So we have this expression right here for the I3, whatever is the result of this one. Okay, 16.875 minus 0 divided by 3. That is the value of I3, which is 5.625 amps. So the only risky thing in here is if your VB is incorrect, okay, if your answer in VB is incorrect, everything now is also incorrect. So just be careful when it comes to solving for the super node voltage in here, which is the VB. Okay, and then for the I2, again, you can use this expression right here, or you can just simply apply KCL, okay, which is, same with this one, I1 plus I2 is equal to I3. So solving for I2, we have I3 minus I1. So 5.625 for the I3 and then 2.625 for the I1, which is now equal to 3 amps. And then from here, we can now solve for the value of VR1 and VR2 and VR3. So VR1 first, so I1 times R1. I1 is 2.625, and then R1 is, where is that one? 5 ohms. So 2.625 times 5 will give us 13.125 volts. Okay, or you can actually use this one. Okay, so going back to our main reference, so we have VA minus VB. Okay, for our voltage drop. Okay, so you can also do that one. So VA is equal to 30 minus VB. Okay, where is our VB? Minus 16.875. So 30 minus 16.875 will give as a result of 13.125 volts. Okay, so please check everything. So I'll give you guys 1 minute to recheck our answers before we proceed to the VR2 and VR3. Okay, so is everything correct? My 15 right here, Miss Chelsea, on the multiplication. Okay, so in here I just multiplied 15 because my goal is again to eliminate our denominators. Okay, so again 15 divided by 5 is 3. So 3 times 30 is 90. And then 3 times negative VB is negative 3 VB. Okay, and then same, so 15 times 3 is 45. And then 15 divided by 3 is 5. So we have here a multiplication of 5. So 5 times VB is 5 VB. And then from here, you can now simplify everything. Okay, just add similar terms, etc., etc., and then you will get this one. All right. So any other concerns? Okay, you're welcome, Miss Maxine. Great. How about the others? Were you guys able to verify whether our answers in I1, I2, I3, VR1 is correct or no? Okay. Why is my PC super lag? Okay. So there's already two of you who already verified this one. Okay, so I hope the others were able to follow. Okay, everything. Okay, so moving on, we have here for the VR2 and then the VR3. So for the VR2, just, as long as you already know the value of I2 and R2, which is 3 times 4, it will give us 12 volts. And for the VR3, so the same method. So I3 is 5.625, and then R3 is 3 ohms, which will give us 16.875 volts. Okay, wherein if you guys are going to take a look at this one, so for VA, VB, and then VC, so VA is 30 volts, and then VC is 12 volts. Oops. My bad. Okay. So see, so at this point, okay, so this is not 12 volts rather, because this one is I2. Okay, my bad. So I mislook on this one as 12. So in here we have to solve for the value of VC, since the only given is 3 amps. So solving for VC, okay, we have here VA, I mean the original equation right here. Okay, and then just substitute everything and then just leave the VC right here since we don't have the value of VC. Okay, and from here we will get this one as a result just by substituting all of the given values. Okay, and then after that, so again our goal here is to eliminate the denominator. Oops, wait a second, what did I do next? Okay, so not yet. I have simplified this one first. So 30 minus 16.875 divided by 5 will give us 2.625. Okay. And then VC minus 16.875 divided by 4 will stay as it is since we cannot do anything about this one. And then in here, so 16.875 divided by 3 will give us 5.625. And then in here, we only have one remaining denominator. So just multiply that 1 by 4 to eliminate this denominator right here. So 4 times 2.625 will give us 10.5. And then 4 divided by 4 is 1. So just copy as it is. So VZ minus 16.875 is equal to, so 4 times 5.625 will give us 22.5. Okay. And then from here, you can now add similar terms. So 10.5 minus 16.875, or what I did here is I transpose everything. Okay, so VC is on the left side, and then everything that is not the same is on the right side. Okay, so in here we have 22.5 plus 16.875 minus 10.5. And then in here, just simplify this one. I mean, not simplify, just solve this one using your calculator, and then you will get 28.875 volts. Okay, so this is the solution using our main expression. Or you can, use the VIR, okay, or the VR2 is equal to I2 times R2, okay, because in here VR2 is VH minus VL is equal to I2 times R2, wherein VH is VC and then VL is VB, so retaining the I2 and R2. And right here VC minus, so VB is 16.875 is equal to 3 for the I2 and then 4 for the R2. And then again, just solve this one and then just transpose this one on the other side. You will get 12 plus 16.875, so which will give us the same answer, 28.875 volts. Okay, so yeah, that's it for this example number 2. So I hope you guys were able to follow on how did we solve the VC. So we have 2 ways for that. Okay, so let me just ask you guys, are you guys able to follow? Is everything clear so far? Okay, so 1, 2, 3. What about the others? All right, so it's a good thing that most of you were able to get this one. Okay, so that's it for this example, and then here's just a conclusion. So generally, nodal voltage analysis is more appropriate when there are larger number of current sources around. Okay, so if we have maybe purely voltage sources, then you can use superposition theorem. But if there are more current sources, then nodal voltage is much more preferred when it comes to solving. Okay, solving for the unknowns. And in here, for more examples and explanations, so again, you can visit those 3 YouTube links. Okay, so this will give you another explanation, another example, to just again to clear up your questions or clear up your minds when it comes to understanding the nodal voltage analysis. So yeah, that's it for this module, and this is already our last module, and we still have one remaining meeting, okay, which will be on Monday. So we will not meet next meeting anymore. So I will give this one as your free day to finish the two quizzes that I gave to you. So the same with the laboratories that I am giving to you guys. So later on, I will add one more laboratory, which is for Maxwell loop method. Okay. So the due date of that one is also May 24. And then your midterm exam will be on May 27, Thursday. So the coverage of your exam is, of course, everything that we have discussed from Module 1 to Module 6. And since we don't have quizzes for, yeah, we don't have quizzes for the superposition theorem and the nodal voltage analysis, so I would highly suggest you guys to, spend a lot of time in doing some practices. So just visit this website right here, visit this site. Oops, my bad. I wasn't able to include a link or a practice exercise for superposition theorem. Anyway, you can find a lot of examples in Khan Academy, okay, or even in YouTube's. So there's a lot of tutorials in there which will teach you different kinds of examples when it comes to superposition theorem and nodal voltage analysis. And also, don't forget to answer this one, the case study number 3. So the due date of this one is also on May 24. All right. So the same with your case study number 2. Okay, so we now only have one minute left. So do you guys have a question so far? Or if none, just give me a thumbs up. Okay. So yeah, those who gave me a thumbs up, you may now go. And yeah, so let's just meet again next week after your midterm exam. Okay. And goodbye and thank you guys for coming. So if you guys have a question in the future, feel free to message me anytime. Okay.